So let's start with quantum Fourier transforms. And just like any other Fourier transform, like discrete or continuous, it's just a change of basis. So if you're like an electronics engineer like me, or if you have gone through Fourier transforms, you'll be quite familiar with it. So forget the quantum for now. Let's take up a normal Fourier transform, which mainly what it does is, if this is a signal in time domain, right, and the amplitude, its Fourier transform will just tell us which frequency component in the signal, the basically the variation of the amplitude in the signal, the variation is considered in one frequency band or the other, like that. So in case of a pure sinusoidal, there is no concept of bands. It's just uh, one single frequency. So if you see here, and if the frequency is 2 pi, then at 2 pi there'll be one discrete sharp hike, which means that all of its variations, the whole signal is basically coming out of that 2 pi frequency. So obviously we don't have pure sinusoidals in real life. We come across complex signals, and that is, you could say that complex signals can be approximated by a series of sinusoidals, by a set of sinusoidals with different amplitudes and different frequencies. So in that case, in such case, if this sinusoidal has a frequency some omega k, say, so the complex signal which has a set of sinusoidals, which is approximated by a set of sinusoidals, omega 1, 2, 3, 4, like that, will have some Fourier distribution, like you could say this, like representing for each k, like k is equal to 1, 2, 3, how whichever sinusoid is there in the approximation represent, like corresponding to that, we have the amplitude in those frequencies. It is a very continuous distribution, actually. I mean, continuous in the sense it is uh, packed with so much sinusoids that they're just like small gaps, and the discrete approximations are very close to the continuous ones. Of course, when we are dealing with computations, we only deal with discretes. So, I mean, this was just a small crash brief about the Fourier transform. And what you need to take away from this is just that in real time we deal with uh, time axis, right? Like the signals are, whether be it a video or audio, all those are dealt in time axis. If it's a picture, then it's on spatial axis. But when we transform it, we want to see it in some other domain, which we want to see it in another perspective that will help us analyze it better. That will give us more hidden information, you should say. Like seeing this signal, you wouldn't necessarily, I mean, this is very pretty easy. You can say that the frequency is 2 pi, but like if you want to see some other complex signal, seeing it in frequency domain will give you a better understanding how it is there, how it is constructed. So let me clear the drawings. And okay, so before that, if any qubit is represented in such manner, you must be familiar with this. And we say that alpha and beta are the squares of these, or the amplitude of these are the probability where the qubit will collapse to state 0 or state 1, right? So any qubit is it can be represented as this. And so when we say that alpha and beta are in complex numbers, the amplitude of complex numbers could be same. Like if I say 1 plus 2i or 2 plus 1i, the amplitude would still be the same, right? Root 5. So uh, what what is the takeaway is that there are many states which are indistinguishable by us because their amplitudes are still same, the probabilities are still same. So in a pictorial representation, this is known as a block sphere, right? So in a pictorial representation, the state zeros and ones are marked in the z-axis over here. And that's pretty obvious. Like any point in this sphere, the projection towards the projection on the zero axis would be that probability, and the projection on the one axis would be its respective probability. But then what is the y and x axis? In this particular representation, we have y axis as the plus and minus I, which is the square root of 1. And in the z axis, it's simply between the probabilities of zeros and ones, right? It's called the plus states and minus states, which like we usually define the plus and minus states, like we also did in the previous session, as the ones obtained by the Hadamard gates. So that in QFT, that we have as the basis instead of zeros and ones. So the Fourier basis for one qubit would be the plus basis and the minus basis, and the uh, like the how to get from 0 comma 1 basis to plus comma minus basis is through an Hadamard gate. These are actually like just definitions. There's nothing like mind blowing about this as such, like till now. These are how do I say? So let me give a mathematical example. But before that, let me set some terms and like some basic definitions. So whenever we put a tilde over here on top of state, that means it's the Fourier representation of that particular state. So if the state is x, then like if a quantum register has the state x, then it's in its Fourier representation, we just mathematically we just represent it as x tilde, right? So now finally getting to the definition, or the the definition of quantum Fourier transform would be this. It is basically the exact same as inverse discrete Fourier transform in our DSP classes. So any state x in its Fourier domain would be represented as 1 over root n, and the summation of here omega n is basically e power 2 pi I over capital N. Capital N would be the would be 2 to the power n. So bear with me. There's a lot of mathematics here, but uh, right, this is just the definition, and its intuition would be more clear later. So 1 over root n, the summation of e power 2 pi I over x over 2 power n into x and y, and the state y. So this will obviously be clear with an example, not like this. So let's just take an example of a generic one qubit QFT, right? So here the capital N is, as I told, the 2 power n. That is basically the total number of states possible with one qubit. So for one qubit, capital N would be 2. So the amplitude normalization factor would be 1 over root 2, and omega, as I said, is 2 uh, 2 pi I is the square root of minus 1. So 2 pi I over capital N. So that would be again 2 pi I over 2. And x we are currently taken as generic x state, and y would be going from 0 to n minus 1, right? So for y is equal to 0, we have one term here, and for y is equal to 1, we have another term there. Here. So anything into 0 is 0, and 0 to the anything to the power 0 would be 1. So the state 0 is unaffected over here, and for the state 1 it is 2 pi I into x. So and by 2, right? So it's just I pi. So that will depend on the state x. Now for x0, so what we are basically saying is for QFT of 0 state, we get 1 over root 2, the state 0 plus state 1. So that is just the definition of plus state. So these are just the definitions here. And similarly for QFT1, if you see, it would be again 1 over root 2 into a state 0 unaffected, and I pi 1. So that e power I pi is minus 1. And so the state would be 0 minus 1 over root 2. That's basically defined as the minus state. So what is to say is, for a 1 qubit QFT, if we just apply Hadamard gate, if you realize this transformation is just the application of Hadamard gate on the qubit 1, we will so basically on application of Hadamard gate, we get the quantum Fourier transformation for that one bit. Another way to look at this exact same thing is, if you have a state alpha 0 plus beta 1. Here alpha and beta are the like alpha square would be the probability for collapsing to 0, and beta square would be the probability to collapse into 1. So these are just measurements coefficients, right? So according to our definition here, the x0 would be alpha and x1 would be beta. X0 x1 means just the like what is the coefficient of zeros and ones, right? And again, capital N would be 2. So here, applying the same thing, we get that 0 y0 is plus state and y1 is minus state. And so why we are looking at this second way of second illustration is that you can collapse it in, like we can get the gate matrix through this way basically. So the unitary again it's the gate, so it'll be a unitary operation. So the unitary matrix, when you collapse down the whole thing, would be uh, this way. So for zero state it would be a plus operation, and I mean plus state. For one state it will be a minus state. And turning it into a matrix here, the first column represents 1 1, in the sense 0 is again unaffected and 1 is also here unaffected. And in the second column, that represents what the output would be when our input qubit is minus when our input qubit is in the one state. Here again the 0 is unaffected and the first state is negated, or I mean not negated, basically it's just rotated 180 degrees, so that's why the minus sign. So again, this is the same conclusion that we got, that the whole operation, the whole quantum Fourier transform on one qubit is nothing but Hadamard gate. So what if the number of qubits are increased? What if we have more than one qubit? Uh, so I'll just show you a reference here. Reference the actually this is a reference from which I carried a lot. So right, this is a Qiskit textbook. And here you can say, here you can again form the intuition that in the above picture we have bits going from 0 to 15 in computational basis, that are zeros and one. If you see, these are flipping from zeros to ones and again to zeros to ones. So that's just what's happening. It's like it's either 0 or 1. There's no in between. But when you come to the Fourier representation of these states, so like if it's 8 tilde, it means the Fourier of state 8, Fourier transform. So here you can see that the qubit 0 goes from plus state to minus s. This is exactly plus state, which I told earlier. The x-axis represents that. So it goes from plus state to minus state. But the other qubits do not uh, flip from plus to minus. They are basically rotating in between. So the rotations are not 180 degrees. They are uh, not flipping 180 degrees. They are having in between intervals. So again, for a larger number of qubits, we have the rotations on smaller angles, so as to say. So we'll come back to this later. I'll this is an interesting takeaway in itself, but for that we'll have to see some of the mathematics again. uh, One more thing. So here for y zeros and y ones, or in this example, so we just expanded the summation, right? We just expanded the summation where the power y, we just replaced it with zeros or ones. But for number of qubits larger than one, we we have like for example, if y is equal to 4 or 5, so we can't just plug in that power over there, because y is basically supposed to be a state which is made up of zeros and ones. It's a state register, you should say. So we need to be careful on that. So we what y basically is if y can be represented as from y1 to yn, and what it means is that this is basically binary from decimal representation, right? So yn would be the least LSB, least significant bit. So like yn into 2 power 0 would be just yn. It'll be 0 or 1. and so on up to, if y1, that is the most significant bit, and if there are n bits, then its power to which it is multiplied is 2 power n minus 1. So in case of this example, when y is equal to 4, the 4 can be represented as 100 in binary, right? So here y1 would be 1, y2 would be 0, and y3 in this case, so would be 0 again. So here we cannot just substitute y as 1 0 or 3 4 like that. We need to actually represented in terms of this summation form. We Because it's binary, it cannot be more than one, right? So like these are all basic things. So after telling you all this, let's go into the final derivation of the quantum Fourier transform into the form in which we can try to develop a kind of a circuit, right? So right, right. So this derivation, again, it's really mathematical, but it's easy to follow. Uh, right. So till the second step, we have done nothing. It's just the definition of Fourier transform. It's 1 over root n and summation over e power 2 pi I over 2 power n into y state, right? And here, like I said, when y is like greater than 1, basically y is consisting of more than 1 qubits for n qubits. It means y should be represented as a summation of individual uh, yks and multiplied with respective powers. Like for here we had y3 y1 be multiplied with 2 power 3 minus 1. So that is 2 power 2, that is 4. So y1 is 1 and 1 into 4 is 4, and others are 0. So instead of representing as just 4, we represent it as 1 into 2 power 2 plus 0 into 2 power 1 plus 0 into 2 power 0. So similarly, here we replace y with this kind of summation, where the summation runs from 1 to n, and like this is basically because we already had it divided by 2 power n, right? So that's what this is. And the state is also expanded in this form, where y is just a collection of y1 to yn, right? These, so this is just again the expansion of the definition. And since the summation is in the power of the basically the exponent, the this is basically multiplication of different terms, right? So because multiplication of e power 1 plus e power 2 would be equal to e power 1 plus 2, that is e power 3. So similarly, since this exponent contains summation, so we take that out and write it in terms of different exponent terms in like in this form. So e power 2 pi like we just take a generic pattern there, and we transform it into this. So if you like see carefully, this is exactly same as this. We're not touching the state part right now over here. We are just we are just splitting the exponent term into multiple exponent term into n exponent terms to be exact. And for each exponent term contains e power 2 pi I and yk over 2 power n multiplied by e power x, right? So now after expanding all that, uh, like you could see that it's okay. So we are trying to write this in terms of like state zeros and ones, okay? So it's like it's represented as sum to a product of exponentials. So this will be the equivalent representation over here. Yes. You had any questions?
No, 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 continue.
Okay. Right. So anyway, so this will be the equivalent representation over here. Here, this sign, this weird sign, this is just a tensor product, which is just like just multiplication, you should say. There's nothing very complex over here. And again, rearranging the same thing, we have like this. Basically, we are just how do I say? We are just expanding the whole summation. We are not having any summation right now. We have expanded it to the n terms. So like we have let me put it. So if you see the picture below, it's of course the same thing as above one, but here it'll be represented as each bit of the input x vector is being transformed individually. So this is a useful observation. It is not even observation, it's just like a manipulation. This is useful to write it in this way so that it'll be easier for us to form the circuit. I'll explain how. So if you have an input x which is x1 to xn, it could be represented as x1 a product with x2 product with x3. What this means is, um, when we have the Fourier transform of x, and we have this whole expression over here, we can see it as x1, the x1 bit, each individual bit being transformed separately on their own. So if we have x1 over here, it could be transformed as 0 plus 2 pi I x1 by over 2 power 1, and x2 over here 0 plus 2 pi I x2 over 2 power 2, and similarly xn transformed independently. So when we have this independence, we can easily like convert this form into a circuit form. We can easily get the gates. So right, like we'll just have a small example, whether you would want to follow this representation of Fourier transform or the basic definition of Fourier transform, you would end up with the same thing over here. If we have n is equal to 3, and that means capital N would be 8, and if we have a random input vector, if it is equal to 5, then it can be represented 101, right? So if you expand it in the definition, it could be represented, I mean, it could be again manipulated and factored in this form, 1 over root n, and here uh, n- like notice the denominators over here, over 2 over 4 over 8, right? So one thing you would want to like remember here again. So these looks like a Hadamard gate, like for example over 2 over 4 and over 8. These are the factors which make it different from Hadamard gate. You don't have a 2 power n factor in the Hadamard gate, right? You just have pi I, I pi. So in the first case, when 2 pi I phi over 2, it's just pi I into phi. That's basically applying the Hadamard gate 5 times. But in such cases, instead of applying one gate plenty of times, we resolve to another approach where we have um, partial rotations. So I'll come to that later. We call them as rotational gates, unitary rotational gates, and they can be used to rotate the qubit partially. So when I say rotate, what do I mean is it's just basically adding phase. You don't like physically rotate the qubit. It's just that when you represent the qubit in block sphere here, uh, like I showed you over here also. So these are the rotations, right? Rotation means it's just adding a phase to them. That's it. And wait, where was I? So if you see there, the qubit over here is being rotated the most, and the qubit over here, since the denominator is larger, is being rotated half of it, and the qubit over here is being rotated the least in this case. So if you see, the rotation of each qubit varies. So the position of the qubit, like of course the value of the qubit is important, whether the qubit is 1 or 0. Other than that, the position of the qubit is also important for applying the appropriate rotation. So that's what's been illustrated in this picture. So for one being in the final least significant bit place, the rotation is such, and when one is being shifted one place left, then the rotation is a little more than the previous one. So this has the least for the first one where all are zeros, this doesn't have any rotations, like I've been mentioning from before. Zeros, we don't touch zeros. And for the bit one, when it is at the least significant bit, so the rotation is least. When it is moving towards the most significant place, the rotations are uh, amount of rotation is increasing. Basically, the phase that we are adding, that is increasing as seen in the denominator, right? Also, one more takeaway here is that when we have all the bits as one, right? So as I said, we don't touch zeros and we rotate the ones. So in that state, when all the qubits are one, so that has the most rotation there as seen by this. So all the terms over here, they get multiplied and the exponents get added up, and the exponent looks somewhat like this, right? So uh, this so using these two takeaways, and like I said, a rotational gate can be introduced, and using a Hadamard and rotational gates, we can somewhat implement the circuit. And let's see how. So the Hadamard gate here flips one from either zero phase to 180-degree phase, that's plus one or minus one, right? And the U rotation gate here, these gates we should define with a parameter k over here. So that k determines the amount of rotation. Higher the k, lesser the rotation. So you could say that when k is 1, U rotation gate is similar to Hadamard gate in terms of rotation. That's it. And here, like, think of this U rotation gate as like, if you just expand this matrix, it's similar to the formulas above. It's just applying a phase of 2 pi I over 2 power k to the bit 1, and it is not touching the zeros. So again, if you want to understand this matrix, the left column, the first column is what the output would be when the input is the bit 0. So when the input is bit 0, the output would be 1 into 0, that is 0, and 0 into 1, so that's again 0. So that means that it is not affecting the bit 0. And the next column would be what the output would be when input is 1. It is again 0 into 0 is 0, and this exponent into 1 is basically adding this much of exponent into to the state 1. So think of it as rotating with the amount 2 pi I over 2 power k. So that's defined by this gate k, I mean this parameter k. So now let's try to come up with the circuit. Again, this is just one form of the circuit. We can have multiple forms of the same circuit. It's just a way of representing it. So now when we have the input vector x1 to xn, so applying the Hadamard gate is basically we are creating superposition. And once we have superposition, then we just applied the rotational gates and try to get the exponent that is represented over here, right? So we want to get this exponent over here. So what you can see is here you have multiple exponents when with rotation over 2, with rotation over 4, with rotation over 8, so with rotation over 2 power and so on up to 2 power n, right? So here we have like naturally we have different UROT gates also, with parameter 2, with parameter 3, with parameter 4, and so on up to parameter n minus 1 and parameter n. So these are to provide us different amounts of rotations. So for the bit x1, again, like I said, since we had this product representation, so we can apply individual gates to individual bits independently, right? So if we only want this one bit to be transformed, then we have first Hadamard gate and successive rotations. And these are again control rotations. These are based on the qubit 2, 3, and so on. So if a control rotation means that when the qubit 2, for example, is 0, then this rotation will not be applied. When qubit 1 is, so when qubit 2 is 1, then this rotation would be applied. So that's just control. And so the least significant bit qubit always depends on the other like more significant bits. So that can be seen when we can analyze q2 also. Again, starting with Hadamard gate, here the rotation depends on q3 and so on. It does not depend on q1. So in order to form the circuit, what we can do is we can first transform this bit q1 first using the first Hadamard and successive rotation controlled by other more significant bits. And after that, we already have our first bit of Fourier transform of that input vector. Then for the second bit, we can do the same. And like in Qiskit also, we can achieve this whole circuit with a for loop, actually, and with two for loops, and yeah, so on. So for the last bit, if you see, it's just one Hadamard gate and no rotations. So in this particular example from which I took this, they are using they are using swap gates also, basically to swap the order of bits in the output. This is not necessary as such. In many papers you can also find it without the swap gate, because I mean, like the output is with you, right? You can just switch, like you can just reverse the order of output in which you want to view it as. It can be done classically also, just replace them, like place them in a different order. That's not a big issue. But then this, for the sake of completeness, they have represented with swap gates here. So again, if you want to analyze this kind of mathematically, initially you have this input vector, and in the step one you're just applying a Hadamard gate, and uh, this is the representation of Hadamard gate. And since we have a tensor product, we can just write gate and then the state. We don't need to fully multiply it and expand it. So we can write it in a very generic way. So in the step two, again, we have a rotation that is applied only for the state one. Uh, right, anyway. Uh, Yeah, so going on. So similarly, when we go through all the steps and write down all the rotations over here, if you see the state zero is not affected, and for the state one, we have a series of exponents that's due to all these rotations. And that is the final form of Fourier transform in terms of circuit, you could say. So this is again another example that I found in Qiskit's textbook. Here the swap gates aren't applied because the initial order in which we are making uh, the transformations is that is only reversed. Like we are starting with Q3 over here, and then applying control rotations with lesser significant bits. So this order can be confusing a bit, but you can just pick any one order and like decide whether you want to apply the swap gate or not. And depending on that, of course, this whole circuit would be in a system, right? So in that system you would get to choose like how to make use of this, whether to apply the swap gate or whether to design the other part of the system uh, in such a way that expecting a reverse Fourier transformed bits. So yeah, I mean, okay, so that's the basic intuition of how to get the Fourier transform circuit out of the definition using some manipulations. So, so this would provide us the Fourier transform.